Let's get started. We did the first half review last week, so we don't have to rush with this week. Are there any, got any questions about any of the problems in the review? Okay. So I'll stick to the ones that I've highlighted, and we're going to pick it up with 34. Okay. Consider change of state descriptions. Select the name of the change of state for when energy is. I knew if I started talking, somebody would come in. When energy is absorbed. I'll finish this one and then deal with that. Okay. Didn't we look at one of these before? Changes of state. So say we have gas up here, and we have liquid over here, and solid over here. And if we go from a liquid to a gas, that's evaporation. Right? And a very specific type of evaporation would be boiling. If it goes the other way, that's condensation. If we go from a liquid to solid, let's see, let's do it inside here. Liquid to solid, that's freezing. And if we go from solid to liquid, that's melting. Those are fairly common. Most people know those. The ones between gas and solid are a little more cryptic. Let's see, if we go inside, go this way. Solid to gas is sublimation. And gas to solid is deposition. Okay? Each one of these either absorbs energy from its surroundings or gives up energy to its surroundings. So, which ones would have to absorb? Something that goes from more ordered form to less ordered form is going to absorb energy because we put more energy into the particles. They're vibrating or moving faster. So if we go from solid to liquid, if we melt that, this is endothermic. By that I mean absorbs energy. Okay, one soldier down. And if we go from liquid to gas, that's evaporation. That's also endothermic. And if we go from solid to gas, this sublimation, that's endothermic. Right, we go from more ordered to less ordered. So the opposite directions would be exothermic. They give up energy. If we become more ordered, lower energy state, then that energy got to go somewhere. So it goes out. That means condensation is exothermic, or releases energy. Let me find a better place for it. Freezing is also exothermic. And deposition is exothermic. I'll put it here. Exothermic means, let's see, means release energy. Okay? So, with that in mind, which one of these changes of state absorbs energy? Let's see. Sublimation would be here. That absorbs energy. Condensation Here it is. That's exothermic. Deposition is exothermic. And freezing is exothermic. So the only one that's right is sublimation. Okay, 36. Characterize the effect that changes will have on the vapor pressure of a boiling point of a liquid by decreasing the temperature of the liquid by 20 degrees at constant pressure. Okay, so changes on vapor pressure and boiling point. So there could be vapor pressure could go one way, it could decrease in its value, boiling point could at the same time increase. So what do we mean by vapor pressure? Right, remember our example here where you have a liquid in here, and at any given temperature it starts off vaporizing, right? But at a certain point we get a return of those molecules. We get enough of them in the vapor phase that they return to the liquid. So at that point we have equilibrium, and there's a pressure that develops in here, and it's dependent upon the temperature. Okay? The boiling point is, let's see, temperature, boiling point is that temperature at which the liquid turns to gas in its body, not necessarily at the surface. Right? So it has to fight this vapor pressure to make that boil. That's why when the pressure over the liquid decreases with elevation, the boiling point decreases. It doesn't take as much energy to get that stuff into the vapor phase. So look at the question. At constant pressure, if the pressure is constant, if the barometric pressure or the atmospheric pressure is constant, then the boiling point is constant. The temperature at which it boils will not change. All right? So that gives you a clue as to which one of these might be the best answer. Boiling point does not change. So it's either B or C. Right? This is test-taking technique. So vapor pressure, does it change with a decreasing the temperature of the liquid by 20 degrees? So we're going to take the temperature down by 20 degrees. What's going to happen to the vapor pressure? It's going down too. Right? So B would be your best answer. Vapor pressure decreases, boiling point doesn't change. All right. Take a look at 38. For the following intermolecular force descriptions, select the correct name from the response list. Okay, so let's review what intermolecular forces are. The difference between intermolecular versus intramolecular. These are internal bonds. They're the ones that hold the molecule together. These are attractions, or in some cases repulsions. between molecules. Okay? So, what forces do we have available? If we're only talking about these intermolecular forces, then the strongest ones are those between polar molecules. Or we could have those with a dipole. One has a dipole and the other one has a dipole. Or a subcategory of that would be, say, dipole ion. If you have ions in solution, then they will interact with the dipoles of the solvent. And then another subcategory of these are the strongest of these. So I'll tell you what, let's put them in order of strength. So stronger than just the general dipoles is hydrogen bonding. Okay? So what happens after that? Well, if your molecules don't have a dipole, then you have nonpolar molecules. And how do they attract one another? All they have available is London dispersion forces. Now, which ones are temporary and which ones are permanent? These are permanent. They're part of the molecule because of the way the molecule is built. These are temporary. Because with a nonpolar molecule, you don't have any access to permanent charge distribution. Right? It's all kind of milquetoast. So the London dispersion forces are temporary because they come in a picosecond and they're gone. But they are significant enough if there are no permanent attractions to deal with, then these are always there. It's just if these are non-existent, then these take over. All right, so the question says we have permanent electrostatic interaction between polar molecules in which no hydrogen is present. All right, so it won't be hydrogen bonding, it'll have to be dipole-dipole interaction. Okay? It's a long way to answer a simple question. Okay, let's see, 40. A solution may contain what? Well, let's see, what is a solution? Remember, a solution is a homogeneous mixture. And it has solvent and solute. The major component is the solvent. Any minor component is the solute. So how much of each can we have? How many can we have? Only one solvent. Right? We can have as many as we want solutes. So to answer the question, a solution may contain what? Only one solvent but many solutes? Well, A is a good answer. B wouldn't fit. Many solvents? D wouldn't fit. Many solvents. C, only one solvent and one solute? No. You can have as many solutes as you want. That's 1 plus. Okay, 41. While we're here, how do we tell the difference between a solution versus a suspension versus a colloid? Remember how we do that? Starts with a T. The Tyndall effect. And where you shine a strong light through the solution, if it's a solution, you won't see the beam going through the solution. It'll come in, it'll go in one end, come out the other, and you can't see it in the solution. But with a colloid, you will see the beam, because a colloid is not a solution. It's based upon particle size. Very small particles will diffract the light so you can see the beam. Now the suspension, you could use a light beam, but a suspension, all you have to do is wait and it'll settle out. But you can use the Tyndall effect on suspension too. If particles are very small but not small enough to stay suspended like a colloid, then you may want to find out before it has a chance to settle. You want to know if it's a suspension or a solution. Okay. Okay, 1 minute. Which of the following statements concern? Oh, I was just digressing. Sorry. I wasn't answering a question there. There's the answer to the question. Moving on. 41. Which of the following statements concerning a saturated solution is incorrect? All right, what do we need to have a saturated solution? Saturated solution. A saturated solution contains maximum amount. And we can define that anyway. We can define it in terms of mass or volume. Maximum amount of solute. Per unit solution at a given temperature. Because if you change the temperature, the amount that you can put in solution will change. It usually goes up as you increase temperature, more you put more in solution. Sometimes it goes the other way. Okay, so let's go back to the question. Which of these are not true concerning a saturated solution? So undissolved solute are the first two words in every one of them. Undissolved solute must be present. Is that true? No. It can be saturated without having any precipitate in it. Undissolved solute, well, that's the bad one. The rest of them are true. May or may not be present. Undissolved solute, if present, is continually dissolving. If we do have a saturated solution, and we have some solid in the bottom, right, there's our solution. What's going on with that solid? It's dissolving and depositing and precipitating. Here's another equilibrium. So if you have undissolved solid in a solution, you're having both processes at the same time at the same rate. So what you see is the amount of solid doesn't change. But on the microscopic level, the activity is furious, going this way and that way. And we don't have time to discuss the evidence for it, but there is a logical, we can follow a progression of steps and prove that that's what's going on. Undissolved solute, if present, is in equilibrium with dissolved solute. I just said that. That's true. So B, C, and D are all true. A is not true. Now, undissolved solute may be present, yes, and that's how we create a saturated solution. Right? We most of the time we increase the temperature, and we dissolve more than we expect to be soluble at the lower temperature. So once we get that in solution, then we set it aside and let the temperature drop. And if it doesn't become supersaturated, we could just drop a crystal in there, and the solid that it doesn't want will precipitate out. And at that point, once it's stabilized at that temperature, you have a saturated solution. If you don't want any solid left in it, just filter it. And then you can have a saturated solution with no solute present in the precipitated form. All right, 43. For which of the following types of ionic compounds are most examples insoluble in water? Okay, for this one, since I didn't have you memorize the rules, you need to look at your, let's see, did I include that here? Or did I give it to you separately? It's not in this document. Have that chart. Okay. Okay. Your copy does have it. That chart. So you can use that chart to see which one of these has the most insoluble ones. And working from the rules is usually what I do. Nitrates. All nitrates are soluble. Right? So if we have these choices, right, nitrate compounds are all soluble. Sulfates, oops, not 3, 2, are mostly soluble. Okay, and you can verify that with the chart. Hydroxides are mostly insoluble. There's one notable exception, sodium hydroxide. Sodium hydroxide is soluble because sodium is an alkali metal, and all alkali metals are soluble. So remember how I had them ordered 1 through whatever. The ones that are above take precedence. So I think it's maybe the second one down is all alkali metals, salts are soluble. And then further down you see hydroxides are insoluble except for that one. Chlorides are mostly soluble with some notable exceptions. Right? For instance, silver chloride is insoluble. Most chlorides are soluble. Okay, so to answer the question is, where most examples are insoluble would be the hydroxides. And you can verify that with your chart. Just look which one has the most grays, and that'll tell you. All right, 45. What is the molarity of a solution containing 16.7 grams of ammonia okay, and 1.5 liter of solution? So this is the mass, and the volume is 1.50 liter. Can we calculate molarity from that? No idea? Don't have a clue? Definition of molarity. Moles per volume in liters. Right? That's not moles. So we have to convert it. How do you convert mass to moles for a compound? No idea? We're going from dimensional analysis. We're going from grams to moles. That means moles has to be in the numerator, grams in the denominator, so they cancel. So when you see grams and moles in a quotient relationship, always think molar mass. So what's the molar mass of ammonia? Right? Nitrogen is 14.01 and 3 hydrogens is 3.03. So we have 1704. Okay? Divide that into 16. It's going to be less than 1. I get 0.90. 980. Yeah, 3 significant figures. Okay, now that we have moles and volume, we can plug them into the formula. Moles per volume of solution, liter. And I get 0.653 molar. Okay? Simple, simple. All you got to do is remember the formula. All right, 46. If 145 milliliters of 2 molar potassium hydroxide is diluted to 1.15 liters, the resulting solution contains how many moles of KOH? All right, this is going to be a two-step problem. Let's put what we know up here. We know that the concentrated molarity is 2 molar. We know that if we take 145 milliliters of that concentrated, right, and we dilute it to a total of 1.15 liters. So the volume here of the diluted is 1.15 liters. Okay. Now, if we use our dilution formula, our equation, then we can find out the molarity of the diluted. But the question is, do we need it? Because we're asked how many moles of KOH are in the resulting solution. So what was that first picture I showed you with when we were diluting? You have the concentrated solution over here, and you're going to make, right? You're going to make a solution over here that is dilute. So we take a volume out of here, volume of the concentrated, put it in here, and this is the volume of the dilute. What's the same on both sides? No idea? The same thing on both sides is the number of moles of the solute. Because we're taking moles from the concentrated side, and they're the same moles on the diluted side. They're equal. So the question is, how many moles of KOH are being transferred? So we don't even need to know this side, we just need to know this one. Molarity equals moles per unit volume. Right? We want to know moles. So moles is equal molarity times volume. And these are both concentrated. But those are the wrong units, right? It needs to be in liters. So how would we convert that to liters? Units are getting bigger. Number has to get smaller. By what factor? How many milliliters does it take to make a liter? 1,000. So this one's going to be 1,000th of that one. 0.145. Right? Unit gets bigger, number gets smaller. So now that we know that, we have 2 molar and we have 0.15 liter. And that'll give us the number of moles of KOH, which should be 0.29. Yep. Moles of KOH. All right. Y'all haven't got to, have y'all got to chemistry in MLT yet?
No, that's next semester.
Next semester?
Yeah.
Okay. I'd be willing to bet they have you do dilution calculations.
Yeah, we're doing it now.
You're doing them now?
Yeah.
Oh, you're doing some microbiology, aren't you?
No, we just
No?
doing, yeah, we're doing hematology, but it's like independent and dependent dilutions.
Okay, okay, yeah. Because if you try to put your blood straight through a machine, it's going to have too many cells in it, isn't it? You got to dilute it.
Yeah.
Okay, next one. 47. I was thinking of, have you done microbiology yet?
No, that's next semester.
Next semester? They might have you do plate counts, right?
Mm-hmm.
And then, do you know if you're gonna do most probable number? That's where you make serial dilutions of your sample in tubes, and you count up to on your dilutions to where you don't see any more culture, and you use that in a formula to estimate the number of cells in the original sample.
They taught us how to do the serial dilution calculation.
Okay.
Just recently,
Okay. Okay. Let's see, 47. A colloidal dispersion differs from a suspension in that colloidal particles tend to settle? No. Are large enough to scatter light? Yes. Right. Well, that's true. B is true. They're large enough to scatter light, but does that distinguish a colloid from a suspension? Are large enough to be seen with the naked eye? No. Large enough to be seen with a microscope? No. Okay, so we're in the situation where we have to pick the best answer, right? It's not the perfect answer, but out of those 4, it's the best answer. Large enough particles to scatter light. Actually, the particles in a suspension are large enough to scatter light. It's just a lot of them are large enough to be seen with a microscope or the naked eye. So we're kind of stuck with picking the best answer, not the perfect answer. Let's see, 48. Compared to pure water, a 1 molar sugar water solution will have a, oh, okay. So what's the freezing point of pure water, theoretically? Freezing point of pure water is 0 degrees C, right? What's the boiling point, the normal boiling point for water? That is, at 1 atmosphere pressure, the normal boiling point is 100 degrees Celsius. Okay? what happens to these values? Vapor pressure first. I don't have a value for vapor pressure for water. Vapor pressure for water at any given temperature. We'll just have to do relative for that one, and these are absolutes. So if you add one mole of sugar, sucrose, to a 1 liter solution, actually to 1 kilogram of water, what's going to happen to each one of these? If you add sugar to that solution, the vapor pressure is going to go down, right? Because at the surface, that's where the vapor pressure happens, at the surface. The molecules are not going to be as numerous. The water molecules won't be as numerous at the surface, so they won't vaporize as efficiently. Plus, there's attraction between those water molecules and the sugar that is not volatile, so that holds them back also. So the vapor pressure goes down when we add a mole of sucrose. What happens to the freezing point when you add a solute? Think of ice creams. Freezing point goes down, right? When you add salt to water, it makes the slurry colder so you can freeze custard, right? So the temperature goes down when you add a solute. But when you add a solute, the boiling point goes up. It takes more energy to get those molecules away from the surface. It's kind of like similar reasoning to the vapor pressure. Vapor pressure goes down, so we got to increase the temperature higher to get it to boil. Okay, so which one of these matches that? Lower vapor pressure would be A, C, or D. Right? A, C, or D. And then if we go to freezing point, boiling point's next, excuse me. Boiling point, out of A, C, or D, we need a higher boiling point. So A's out. It could only be C. Let's see if C also has the right lower freezing point. Yep. So that's it. C is your answer. Let's see, 49. What is the freezing point for a solution containing 1 mole of sodium chloride dissolved in 1 kilogram of water? Okay, how do we do that? Well, if the freezing point, the normal freezing point of water is 0 degrees C, and we want to know the freezing point of the solution, what formula can we use? We can determine what the difference in the freezing point is. Right? All we need is this formula. Change in the freezing point is equal to the freezing point constant for water. Let's see. Freezing point constant for water times, let's see, this is going to be in degrees C, kilogram per mole. So if we want to change in temperature, we need moles per kilogram over here. So that's mole. This is moles per kilogram. So the moles cancel, kilograms cancel, and we got degrees C. Now the other thing that we can introduce there is Van Hoff correction, the I. Do we have an I for this problem? 1 mole of sodium chloride produces how many moles of ions? 2. So the Van Hoff correction is 2. All right? Does everybody see that? Yeah. Okay. I looked up K. It's not in there, so I looked it up. It's 1.86. The K value is 1.86 degrees C kilogram per mole. And then the molality is what? 1 mole per kilogram, right? It's right there. 1 mole per kilogram. Per kilogram. There we go. So the change in temperature of the freezing point would be 2 times 1.86, which would be, let's see, 12, and 1 is 6, 17, 1 and 2 is 3. That's the change, degrees C. So it's a freezing point depression. So the temperature, the freezing point temperature, is actually going to be minus 3.72. Because we're starting at 0, we're depressing it that much. So that's why D is the answer. A and B are thrown in there because if you miss this right here, that's the wrong answer that you get. What if I changed it to 1 mole of sucrose? Does sucrose dissociate when it dissolves? No. So its value would be 1. So 1 mole of sucrose would only be minus 1.86 degrees. What if I put calcium chloride? Calcium and 2 chlorines. So there'll be 3. 3 times 1.86. That's why calcium chloride and magnesium chloride both are more effective melting agents for ice on your walk than sodium chloride is. The problem is economics. Right? If you're going to put salt on the roads in the winter, you can't afford to put calcium chloride out there. It's way too expensive. But for homeowners, you know, I throw calcium chloride on my concrete walkway because it doesn't damage the concrete. You put sodium chloride out there and in the spring you'll have pits in your concrete. You have to go out there and patch them. There's an ion exchange, right, between the calcium and the sodium, and the sodium substitutes for the calcium, and the calcium comes out of your concrete during the winter because of that sodium. And then in the winter, there's no calcium there. There's sodium. Sodium dissolves, goes away, and you got a hole. That's the simple explanation. I suspect engineers would be more complicated. In fact, Vincent might have a better explanation. Talk to him about physics. 50. Okay, that one's going down. Crenation of red blood cells occurs when the cells are placed in what? What's crenation? If you start with a normal blood cell, what does it look like when it crenates? Yeah. It kind of shrinks and gets bumpy on the skin because it's losing water. Water is going out. Why would water go out of a blood cell? What type of solution would surround that cell? Hypertonic. Hypertonic, yes. Higher concentration of salt or dissolved solids lowers the water concentration out, so the water pressure movement is toward the outside. So C, our hypertonic solution, would be the answer. I don't know what there's no term for water going into the cell, is there? Well, yeah, for the solution. It swells.
And they burst.
Yeah, but there's no special name like crenation.
No.
Yeah. You get bursting red blood cells and dead patients. Okay, 51. Yeah, that was not working good either. Try one of these. Which of the following solutions is hypertonic with respect to blood? Okay, we've got mass, volume. Mass of sodium chloride or glucose per volume. Okay, let's start from isotonic. What's isotonic sodium chloride? 0.9%. Sodium chloride is isotonic. And glucose,
Oh, you rounded it, didn't
yeah, I rounded it.
you? Okay.
What should it be?
0.87.
87?
Yeah.
Okay. That's better. Yeah, I like that better. How about glucose? You ever heard of this one? D5W. That's
Very rare. Yeah.
dextrose 5% by weight.
One time.
Okay.
Yeah.
So 5% would be isotonic, 0.87 would be isotonic for sodium chloride. So let's compare these. Which of the following is hypertonic? That is higher concentration. Right? So 0.5 is lower, 0.7 is lower for sodium chloride, 4.5 is lower, 7.6 is higher. So D is your answer. Every EMT knows this one right here. And they know when not to use it. Right? If your patient's wearing a diabetic bracelet, you don't give them that, or they'll be dead before you get to the hospital. Now there's some other carbohydrates, sugars that are what they call glycemic. That is, they're not metabolized as quick, so you might get away with that one. Lactated ringers, I think that's why they use the lactose instead, because it's not metabolized as quick. But still, you got to be careful. Monitor your patient. If you have to give them that, monitor their blood sugar. No more than every hour. Right? I'd do it quick. I'd do it sooner if the hospital would let me. There's always that money thing hanging over them. Okay, which of the following statements about solutions is correct? Try this one. Talking solutions. A solution is a homogeneous mixture. Yeah, A is true. A is true. How about B? It is possible to have solutions in which both solute and solvent are solids. Oh yeah. I think brass. You know, copper and zinc. That's a solid solution. So all those horn players in the back of the band are playing solutions. Let's see. Solutions readily separate into solute and solvent if left undisturbed for 24 hours. Oh no. Definition of a solution is it will not separate. But more than one is correct. Right? So D is your answer. All right, 53. A crystal of solid sodium chloride is placed in an aqueous sodium chloride solution. Okay, let's draw a picture. So here's our sodium chloride aqueous solution. And we put a crystal of sodium chloride. It's going to be a cube. Let's make it big enough so we can see it. Okay, it's observed that most, but not all, of the crystal dissolves. Okay, so over time, that crystal shrinks. But it shrinks to that size and then it stops shrinking. Okay, at that point, that solution is saturated. But before we put it in there, it was unsaturated. Right? The solution had to be unsaturated to take more of the sodium chloride than it already had. Okay. All right, 54. This one's not going to last very long either. Consider the following substances and their polarities. Okay, A is polar. A is polar. B is polar. C is nonpolar. And D is nonpolar. Okay. It is true that A is more soluble in C than B. Is that true? Nope. A is false. Like dissolves like. A is more soluble in B and C is more soluble in D. So B says C is more soluble in D than in A. That's true. Okay. Since we have some wonky ones, more than one correct and none, we got to check out C also. So C says D is more soluble in B. Nope, than it is in C. That's false. So B is the only possible answer. Hey, sign in. It's right behind you. Let's see, I think I have some papers for you. Let's see. I also have one for Isabel. Dave, right? Yeah. All right. Let's see. Dave, I don't have your chemical change lab. All right. Let's see. Let's go on. Let's do this one. Oh, we did 54 already. Okay, 54 is gone. Moving on. '55. In which of the following sets of ionic compounds are all members of the set insoluble in water? Okay, so for this one, go to your chart, right, and see which ones are all insoluble in water. All right. For the first one, silver chloride and lead 2 chloride, I believe, are insoluble. Let me see. I'm going to speak out of turn. Lead, where's lead? There it is. Yeah. So silver and lead chloride are insoluble. Ammonium chloride is soluble. Right? All ammonia salts are soluble. So this one only has 2 members that are insoluble. It has 1 soluble, so we can't use that one. How about the carbonates? Calcium carbonate, I think all the carbonates are insoluble. Carbonate, where is the carbonate? Here we go. Carbonate's the second one from the bottom. You look across, the only 2 that are not soluble are sodium and potassium. The rest of them are insoluble. Right, we don't have any sodium or potassium there, so B is a good one. Okay, and let's see, more than one correct, so let's look at C. Lead sulfate, iron, lead 2 sulfate, iron 2 sulfate, and barium sulfate. So let's find the sulfates. Sulfates, here we go. So, sulfates, lead, iron, and barium. Barium's insoluble. Lead's insoluble. And iron is soluble. So we've got 2 insolubles and 1 soluble, right? So we can't use this one. That means that's the only one where all of them are insoluble. All right. 61. Are we getting close? I haven't been keeping track. How far do we go? We're not far. Then we can talk about the lab. Which of the following solutions has an osmolarity of 3? So we're looking for an osmolarity equal to 3. So what's the relationship between osmolarity and molarity? It's I. If I equals 1, osmolarity and molarity are equal. Okay? And if I equals 2, then osmolarity equals 2 times molarity. Okay? And the trend continues. Okay, so let's go back to our question. Osmolarity of 3. So, either we have an I of 1 and a molarity of 3, right? Or if we have an I of 2, then our molarity would have to be 1.5 times 2 would give us 3. So let's see. 4 molar glucose would be 4 osmol. So A's not it. Right. 2 molar sodium chloride would be 4 osmol because sodium chloride breaks up into 2 parts, right? Right, so that's not it. 1 molar sodium phosphate. How does sodium phosphate break up? It breaks up in solution, right? It breaks up into 3 sodiums and 1 phosphate, right? So that's 4 particles. I is 4, and if it's 1 molar, it would be 4 osmol, right? So none of those are correct. Okay? All right. '62. In which of the following pairings are the terms closely related? Okay. We've got pairs of terms, yes. A, B, and C, and then D and E are wonkies. A, B, and C. So are they closely related? Hemolysis? Oh, this does describe what happens to the cell. It just doesn't talk about what there's not a name for swelling. But if we put this in a hypotonic solution, hemolysis will occur. Okay. Lysis means cut or break. So the red blood cells are cut. So hemolysis and hypotonic, those are related. Yeah, that's a good one. How about B? Hypertonic and higher osmotic pressure than within the cells. Yep, that's true. So hypertonic and greater than intracellular concentrations. That's true. So we got a couple. It means more than one, right? Isotonic and crenation. No, that's false. Can't work. But D is two of those. Oh, I wondered when we were going to get to one of these. We got three statements. We have to decide which of them are true. Let's see, 63. Excuse me. So let's see, we have 1, 2, and 3. Okay. Equal volumes of two solutions of the same molarity contain the same number of grams of solute. That's the tricky part. They have equal moles of solute, but not necessarily equal grams, because it could be a different compound. So that one's false. Hemolysis and crenation are opposite processes. Yep, that's true. The solubility rule, like dissolves like, is not adequate for predicting the solubility of ionic compounds in water. The solubility. Predicting the solubility. What do we mean by solubility? How much will go into a given volume of solution? So that's true. Like dissolves like doesn't predict that. It can tell us that in most cases, right, a polar compound will serve as a solvent for a polar solute. But it doesn't talk about, so is not adequate. That's true. So we do have two that are true statements. Let's see. How about 65? Let's see. 1, 2, and 3. Excuse me. Addition of 40 milliliters of water to 10 milliliters of 8 molar sodium hydroxide will produce a 2 molar sodium hydroxide solution. All right. So for this one, we need our dilution equation. Right? M concentrated, volume concentrated, M dilute, volume dilute. So the concentrated is 8 molar, right? The diluted, we're not sure yet. We claim that it's 2 molar, but we don't know. And then the volumes, we take addition of 40 milliliters to 10 milliliters. So we're taking 10 milliliters of the concentrated. What's the final volume, though? 50 milliliters. 40 plus 10. Okay, so now we can say, right, MCVC divided by VD equals MD. I just took the VD from over there and put it over here. Excuse me. So 8 and 10 divided by 50. So that's 80 divided by 50 is what? Or 8 divided by 5 equals 1.6, right? All right, that's not 2, right? So 1 is false. Henry's law is a pressure solubility relationship of gases in liquids. Yeah. As we increase the pressure, Henry's law says we increase the concentration of the gas dissolved in the liquid. That's a true statement. Boiling points are the basis for the solubility rule, like dissolved like. No. Boiling points don't have anything to do with the solubility rule. All right, so we only had one. Only one of the statements is true. All right. Moving on. Oop, got another one. 66. First one. 2 liters of 6 molar solution would contain 12 moles of solute, independent of the identity of the solute. 2 liters. So, if we want to know the number of moles, it's molarity times volume. Right? So, if we had 6 molar times the volume, which was 2 liters, we would have 12 moles. That's true. Number 2, for liquid-liquid solutions, volume of the solution is always greater than the sum of the volumes of the solute and solvent because of solute-solvent repulsion effects. No, sometimes it shrinks. Yeah. That's why when we do molarity, we dilute to a known volume. Because if you just based it upon the additive volumes of the two, the solute and the solvent, you could be wrong. Especially if it's an endothermic or an exothermic reaction. Right? If it's endothermic, solution's going to get colder and shrink. Right? If it's exothermic, it's going to get hotter and expand. Right? So 2 is false. Can't be true. Osmotic pressure is the amount of pressure needed to prevent the process of osmosis from occurring. Yeah, that's one way of putting it. Right? When do we use that fact in the real world? Reverse osmosis. If you take brine or salt water and push it through a system of membranes, semi-permeable membranes that only pass water, then you increase the pressure above the osmotic pressure of that solution, then you would drive water back through the membrane. Right? The osmotic pressure is the equilibrium point. So you exceed that pressure and you can purify water with reverse osmosis. Okay, so we had 2 true would be B. 67. Okay, back to the real normal world, I should say. For the set of ionic compounds, sodium nitrate, potassium nitrate, ammonium nitrate, choose the correct characterization of their solubilities in water from the response list. Oh, all soluble, 2 soluble, 1 soluble. What's the solubility of these guys? All nitrates are soluble, for one thing. All ammonia salts are soluble. And all alkali metals are soluble. Right? They're all soluble. Right? And you can verify it with your chart. I don't think I didn't include the rules on the chart. No. I wanted to make the chart bigger, so I left the rules off. Okay. 67, 68. For the set of ionic compounds, lithium chloride, silver chloride, magnesium chloride. Choose the correct characterization. All right. Most chlorides are soluble. Right, you can see that from your chart. Right, if you just go down here to the chlorides, right, and go across, you'll find only silver, mercury 1, and lead 2+. All right, silver is the only one in that group of the chlorides that is insoluble. So the other two are soluble. That's why B is the answer. Okay. And we ought to be getting close to the end. Maybe we are at the end. There's a lot of repetition in here. Oh, here's another one. 8. Didn't we do one like this before? Characterize the osmotic pressure for a 0.8%. 0.8% mass volume magnesium chloride. Okay, 0.8% magnesium chloride. So, if we go back to, what was it, 0.87 sodium chloride? Okay, 0.87% sodium chloride. Okay, this one is less percent by mass than sodium chloride, but it produces an extra. This has an I of 2. This has an I of 3. So in order to be equal to that one, this would have to be a third less. All right, so this is hypertonic. It's a greater ion concentration than isotonic sodium chloride. Okay? That's how I figured that one. And that's it.